All right, shall we get started? As soon as you take your seats anyway. So it's the last lecture today, right? That's good. We're not completely done yet. This is still the final. It's next Monday, right? It's in the LRSM in the Material Science building just across the street, if I remember correctly. I pushed back a little bit the Project 6 due date. Some people are struggling with some other deadlines, so the new deadline is on Thursday, but I encourage you not to wait until then because you still want to spend some time preparing for the final. Some people were also asking me for some practice problems, so I'll try to prepare something. I haven't really done anything the last year, but I will see if I can do something for you. It's not that much time to prepare for it, but you should be fine. Yep.
Would it be possible to have a review session on Friday?
On when?
On Friday, a review session.
Well, we don't have anything scheduled, so.
Would it be possible to schedule something?
I can look into that. I cannot promise that because it's difficult to schedule something at the last minute. What I can do more likely is to post some practice problems and then solutions to that. Okay. So what I would like to do today would be basically finish SVD, single value decomposition, and then we are done. I'll maybe show some applications to it. So this is the SVD theorem, which we discussed the last time. So it says that for any matrix, which can in general be rectangular, m by n, you can always find orthonormal matrices. This means an m by n orthonormal matrix U, n by n orthonormal matrix V, and a sigma matrix, which is rectangular, the same dimension as A, and a special type of format that it has non-zero values only on the, I guess, main diagonal, or whatever you want to call it, and zeros everywhere else. Here are also zeros. Furthermore, these non-zero values that are called single values, and they are ordered. So the first one is the largest one, and they are decreasing, and then you just get zeros at the tail. And the number of these single values is exactly the rank of the matrix. This sigma r here is this r here, which is the rank of the matrix. Okay. If the matrix is short and skinny, then it looks exactly the same way. It's just tall and skinny. Sorry, it's just short and tall and skinny. And the SVD is a factorization of the matrix in the sense that if you do the product U sigma V transpose, you get back the matrix A. Okay. And previously I was telling you like why this is always possible and how to find it. That it's related to the eigenvectors of AAT and ATA. Okay. And today I would like to show some simple examples of SVD just to give you a little more intuition that this is no magic, that it's actually relatively simple. It's nice because it basically combines together all the things from linear algebra we had before. So on one hand, it's simple because it's just a collection of things we had before. On the other hand, it's like everything together. So you just make sure not to get confused. And I think that the easiest way to do that is to just work through a few examples. So that's what I'm going to do now. So let's find SVD of this matrix. Okay. The task is compute SVD of that. Okay. So that's a 2 by 2 matrix. You can already see what is the rank of the matrix, right? I guess we can do like a little bit of a review session like right now on these examples, right? Like these will be like simple questions. You'll probably get 2, right? That's the rank of the matrix quite easily. So how do we compute SVD? Well, the last time we said that the key to computing SVD is to forming these matrices, ATA or AAT, that they are quite closely related. So let's compute ATA. So how do we do that? Well, we just do the product, right? So we do A transpose, so that's this, just 1 here, and that's just A. So if you compute the product, again, in the final, you might have to do like a little bit, maybe actually not so much, less so than in the midterm, but should be able to compute things anyway. So this would be 4, 5, right? This would be 4 minus 1, that's 3. This is again, has to be symmetric, right? So I can already write 3 here. And this is again 4 plus 1 is 5, okay? So this is the ATA matrix. And to compute the SVD of the original matrix, we know that we need to find the eigen decomposition of the ATA matrix. That means find eigenvalues and eigenvectors of it, okay? So meaning now we need to do EVD, eigenvalue decomposition, okay? So how do we do that? Well, you should know how to do this. So I will not go through that again. I will just basically show you what do you get. So the lambda 1, the first eigenvalue will be 8, and the corresponding eigenvector after you normalize it, 1 over square root of 2, you get this as an eigenvector. I hope everybody knows how you would compute it, that you would form the characteristic polynomial, you would find the roots, you would get these eigenvalues, and for the eigenvalues you would find the corresponding eigenvectors. We have done this a few times, so I think it's no need to recap this. So the second eigenvalue is 2, and the corresponding eigenvector is this one. Okay. So why do you think I put there the 1 over square root of 2 with the eigenvector? So we know that the scale of the eigenvectors doesn't matter, right? So why do I bother with the ugly square root of 2 thing there? Yeah?
To make an orthogonal.
Exactly, yeah. You can also immediately see that they are orthogonal, right? That if I do their dot product, that they are, because ultimately I'm looking for SVD, so I need these matrices to be orthonormal, so I can as well normalize it straight away, okay? So you can notice, so these two vectors are orthonormal. And that's what the theory guarantees us, because this is a symmetric positive semi-definite matrix. In this case, actually positive definite, right? You can immediately see it from the eigenvalues. So the theory dictates that there must be a basis, orthonormal basis from eigenvectors. Okay, so cool, everything seems to work just fine. So then those would be the right singular vectors ultimately. To compute the left ones, we need to compute a BI, okay? Because if you remember the picture in 2D, I think that's what I ended with on Wednesday, was that basically geometrically, I don't know how much do I want to go into that. What you are doing geometrically, you are finding an orthonormal basis in the source space. In this case, they are both R2. So which maps by the mapping A or onto another orthogonal basis. Now this time the scales can be different, but there has to be a right angle. And if this is V1 and V2, this is not to scale, by the way. This is just generic picture. This would be AV1 and AV2. Okay. So let's take a look at what is AV1. But it's just simple, you just multiply by the matrix, right? So the 1 over square root of 2 I can just copy there. And here I basically just sum the columns here. So I will get 4 and 0, okay? And this is basically because this is 4 divided by square root of 2. So this will be 2 times square root of 2, 0. Everybody sees that? And this thing is almost the left singular vector, okay? I hope you remember the relationship AVI equals sigma I UI. That's the relationship between the right singular vectors, left singular vectors, and the singular values, okay? Maybe let me give this the arrows to make sure, to make it clear that these are vectors, and this is the singular value. Oh, focus is not as good as it could be. Matter? So here we almost computed the left singular vector. Why almost? Because the UI also has to be length 1, right? Unit length. So basically the U1 is just normalized version of AV1. So that's this, right? Which is how much? Something very simple. 1, 0, as simple as that. And this immediately tells me what is sigma 1, right? That's, somebody wants to say it, just yell it, that's fine. Exactly, that's my first singular value, okay? So that's the first, I guess, triple singular value left and right singular vectors, okay? So this is the left singular vector is actually very nice, it's just 1, 0, and the right one is 1 over square root of 2, 1, 1. Let's do the same thing with V2. So if we just multiply V2 with A, so basically again, this picture, the V2 gets mapped somehow with A, and that's just the scaled version of the left singular vector. So let's do that. So it's going to be 1 over square root of 2, and now we're multiplying A with V2. So how much that's going to be? Well, it looks like we will get 0 on the top and 2 on the bottom, right? Everybody agrees? A times V2. So this is 1 over square root of 2, so this ends up being just a square root of 2, right? So if I again normalize it, how much is going to be U2? So again, U2 is a normalized version of AV2. That's 0, 1, and sigma 2 is, of course, square root of 2. That's the scale I need here, okay? So now I can write down explicitly the SVD of A. So this is my A matrix. Then the U matrix, the matrix of left singular vectors, is going to be actually very simple. So the first column of it is 1, 0. So I'm writing U1 here, okay? And U2 is 0, 1. So it turned out in this case it's actually the identity. Well, that's perfectly fine orthonormal matrix, no problem. So that's my U. And this would be the U1. This would be the U2. The matrix of singular values, that's sigma 1, that's 2 square root of 2, 0, 0, and here sigma 2 is the square root of 2, okay? So this is my sigma. And finally, what is the last bit here? Here I have V transposed, okay? So V transposed is going to be a matrix with the vectors V1 and V2 as rows because it's transposed, okay? So there is a scale of 1 over square root of 2 because both of them are scaled by 1 over square root of 2. And the first row is going to be V1, so it's going to be 1 and 1. And the second row is going to be minus 1 and 1, okay? So here, this first row is my, I guess, to be really pedantic, I should put V1 transposed, right? And the second row is V2 transpose, okay? So it's a column vector, but I take the column vector and I do this to it and I put it there. Cool. I can almost animate things here, huh? And you can verify that if you multiply this together, you indeed get back the matrix A. Unless I have done some horrible mistake. You can also immediately see that the matrix, both the U, of course, orthonormal, right? And V is also orthonormal. That's why there is the scaling factor, so that the rows and consequently also the columns have norm 1, okay? And now we have the SVD. I mean, the null spaces here are trivial, right? What are the null spaces here? Don't say nothing, or don't say empty, because the subspace is never empty, right? Because there is always at least a 0 vector, right? So you cannot really say empty, but it's trivial. It's just 0. It has a dimension 0. So the null spaces, I will show in a second another example where the null spaces actually will be non-trivial. But here the null spaces basically don't show up because they are trivial. Okay. What about the uniqueness of SVD? If you remember this, if I ask you the question, is this the only SVD of A? What would you tell me? That it's not, right? So what I can do to it? Yep, go ahead.
You just change the sigma values.
I can flip them, right? So I could basically permute everything. I could flip the first column with the second column. I could flip the order of the single values, and I could flip the first row with the second row. I would get another perfectly valid SVD, right? That's one thing I can do to it. There is another thing which we discussed at length on Wednesday. What we can do to it. Yeah, I could easily put here minus 1, right? And I could negate the first, I could do this, right? That would still be a perfectly valid SVD. And I could do the same thing on the second one. And that's it. So it's unique up to these funny transformations. Okay? All right, so that was one. I hope you agree with me, a simple 2D example. Let's take a look at another 2D example where the null spaces actually show up. And you can also consider it a practice problem for your final, because it's just basically a simple linear algebra problem. So let's take a matrix like this, fairly innocent matrix. So first of all, what is the rank? I expect an answer immediately. That's correct. That's 1. And let's take a look, just again for the sake of practice, let's take a look at the at the 4 fundamental subspaces of this matrix. Okay, so we will first write them. We'll just first like figure them out just by looking at it. It's just such a simple matrix. Okay, and then we will do it using SVD, and we will hopefully see that they match. Okay, so first, what is the row space? I want you to shout it at me before I finish it writing. So what is the row space? It's a linear subspace generated by the rows of the matrix, okay? So what vector would be generating it? You have multiple choices. I'm fine with you, whatever.
1 over 2 and 1 over 2.
Yeah, I'll make it even simpler. I will just make it 1, 1. Okay. You might want to transpose it so it's like row space, but that's just a cosmetic thing, right? So the dimension of the rows, if somebody has some issues with that, then please ask. I think this is something you should already know. The dimension of the row space, of course, is 1, right? How about the column space? What would be the vector generating the column space? Well, 1, 0 wouldn't be good, right? 2, 1 would be better, right? Because what we need, well, I mean, that's what the columns already are, right? There's nothing you could multiply 0 with and get back 1, so the 0 would not really work. And the dimension, of course, also 1, right? Dimension of the column space, also 1. Third, the null space. So here you need to think just a little bit harder. What is the null space of the matrix? Correct. That would be 1, negative 1. Or minus 1, 1, right? Whatever non-zero scale you want to multiply with. And indeed, that's again dimension 1, right? If you remember the 4 fundamental subspaces theorem, the dimensions has to add up to the dimensions of the matrix. This is a 2 by 2, so here the dimensions are trivial. And the left null space, what is that? Generated by. So that means I'm multiplying from the left, right? So who sees the answer?
1, negative 2.
Correct. 1 minus 2. Let's see, at least one of the correct answers, right? If multiply again by the scalar. Okay, so here we can like directly just by looking at the matrix, you don't even have to compute anything. You can just like blur it out. So let's see if we can find the same result using SVD. Okay, so let's compute the SVD of this matrix. Now it's going to be a little bit different than the previous case because the null spaces have to show up. As I discussed before, the null spaces do show up in the SVD. So let's do just like before. Let's compute ATA. So let me make this a little bit quicker. So this is going to be 4 plus 1 is 5, right? Here it's going to be also 5, and the rest is symmetric. So this is ATA. You can immediately see that the rank is also 1, right? And that should not surprise you. If you were, at least if you were paying attention the last lecture, when I was arguing that the null space of A is the same as the null space of ATA, so certainly they must have the same dimension. So yeah, so no surprise that this is rank 1. Okay, now we turn the crank and compute the eigenvalues and eigenvectors. So if we do that, we will find eigenvalue number 1 is 10. And what do you think is going to be the eigenvalue number 2? If they are ordered by magnitude. So the lambda 1 was the bigger eigenvalue. The lambda 2, you don't even have to compute anything here. That's a hint. That's right. Because it's singular, right? The matrix. The matrix is singular, there must be an eigenvalue 0, but I already told you the 1 is 10. The second one must be a 0, right? If it wasn't, then there would be something terribly wrong. So what about the eigenvectors? So the v1, that's the eigenvector corresponding to lambda 1, it will be 1 over square root of 2, 1, 1. And I guess you could check it if you want it, right? So let's forget about the 1 over square root of 2. So if we just hit this matrix with 1, 1, then we get 10, which is 10 times 1. So that's good, right? The same, the second row is just the same. So there's like nothing going on. So v2 would be, again, 1 over square root of 2. I'm again normalizing them for just like before, and minus 1, 1. Okay? Actually, it turns out that the eigenvectors happen to be exactly the same as the matrix we had before. And I guess that's because I'm looking at such a simple examples. But that's fine, right? The matrix is still different because the eigenvalues are different, right? So it's just a fun fact. Okay, so I guess let's do it a little bit differently now to try things a little bit differently. So what are the singular values of the original matrix? So here we have eigenvalues of ATA. What are the singular values of A? Can you tell me that immediately? What is going to be sigma 1 and sigma 2? There's nothing complicated about it, if you remember. Because the relationship from the last lecture on Wednesday. The single values are simply square roots of the eigenvalues of ATA, or equivalently AAT. Okay, so the first single value is just the square root of 10, and the second one is just 0. Okay, again, to make it a little more interesting, let's now compute the left singular vectors by taking the eigendecomposition of AAT. Actually, in this case, we sort of have to, because in this case, we need to be a little bit more careful than the previous one. In the previous case, we had trivial null space. Here we have non-trivial null space, so we have to be a little bit more careful. So we do AAT. So how much is AAT? Let's just do it quickly. So that's 2, 2, 1, 1. And here we get 2, 1, 2, 1, right? So the AAT will be 4 by 4 is 8. This is 2 plus 2, that's 4. And here it's going to have the also 4, and here we'll have 2. Okay. What are going to be the eigenvalues of the AAT matrix? Here again, if you know the theory, you don't have to be computing anything. You can just tell me what the eigenvalues are going to be. And the answer is simple. They have to be the same as the eigenvalues of ATA. That's what we discussed. Again, I can't repeat everything if I want to finish. But that's what we discussed on Wednesday. Okay, you can go back to YouTube if you don't remember that. We proven that the eigenvalues of ATA are exactly the same as the eigenvalues of AAT. So here the corresponding lambda 1 is again 10, and the lambda 2, of course, again 0, because again this is rank 1. Okay, has to be rank 1. So, and the eigenvectors of AAT, they are going to be the left singular vectors of A. In this case, the first one, the one corresponding to lambda 1, that's going to be 1 over square root of 5, 2, 1. And U2 is going to be, again, 1 over square root of 5, 1 minus 2. Okay, so if you put this all together, I can write down the SVD of this matrix. So how do I do that? Well, first the U matrix, okay? So both is scaled by 1 over square root of 5, so I just put it outside. And here I have my U matrix, so I put U1 first, so that's gonna be 2, 1, and then a U2, that's 1 minus 2. So this whole thing is my U matrix. And please check that it's orthonormal. So first orthogonal, right? And both of the columns have length 1. That checks out, that's fine. Now, what is gonna be in the sigma matrix, the matrix of singular values? The singular values, right? Sigma 1, which is square root of 10, 0, 0, 0 here. This is sigma 2, that's the 0 here, right? And finally, the most interesting part, this is gonna be V transposed, okay? So the V transpose has V1 transpose as the first row. So first of all, there's gonna be the scale factor 1 over square root of 2. And the first row is V1 transpose. That means 1, 1. The second row is V2 transpose, which is minus 1, 1, period. So this is V transposed, okay? And now, the cool thing is that you can immediately see all these null spaces in the SVD. That's what we discussed before, okay? So let's look at the first column. What is that? The U1 vector. That's the vector generating the column space, okay? What is this other guy here? So basically, let me put it like this. So this is basis vector of the column space. What is this one? 1 minus 2. I mean, if you just do pattern matching against this, you immediately see the answer, right? So you don't have to think very hard. So this is the left null space, aka NAT. Okay. Now here, when we are looking on the V, this is V transpose, so we are looking on the rows. So we are looking at the first row. So what that is, well, that's obviously the basis vector of the row space, aka CAT, okay? And the final one, what is that? That's a basis vector of the null space, okay? So here you see beautifully the 4 fundamental subspaces theorem in action. That's what I was previously like explaining in general. So here you see it on like one particular matrix. I guess that's as simple example as it gets to illustrate this. Sounds good. So basically computing SVD is not much more difficult than computing eigendecompositions. That's I guess the message from these examples. But it's extremely useful because it gives you a complete information about the matrix. All right? So in the following, I would like to give you a little bit different perspective to SVD because you might still be a little bit confused because it feels taking this ATA and AAT to compute the SVD feels a little bit like magic. I mean, it works, and we can prove that it works, but it might not be completely intuitive why that's the case. And there is a beautiful intuition behind SVD, which I haven't discussed yet, and I would like you to know that. So that's basically the variational approach to SVD. So variational is just like a fancier term for optimization. We already talked about some optimization problems, like least squares. That's the simplest case of optimization. The difference means variational usually means like in the context of function analysis, when you are minimizing something with an infinite number of degrees of freedom. You don't have to bother about that. That's not the case in what we will be doing here. Here it's just like a fancier term, or that's what people usually use to refer to these things. So let's assume I give you the following task, okay? I give you a matrix A, which is some important matrix that matters to me, maybe some data I measured or purchased somewhere, okay? Or maybe it's an image or just something with some relevance to you. And the task is to find vectors X, which would be an m-dimensional vector, and Y, which would be an n-dimensional vector, such that the Frobenius norm of the difference between A and xy transposed is minimized. Okay, so this is a Frobenius norm. So what I'm asking, so we are given a matrix, and I need to find two vectors such that when I do the outer product xyt. So first of all, let's spend a minute talking about the outer product xyt, right? So the xyt, what is it type-wise? Okay, that's such a simple question that it's not even worth asking you. That's an m by n matrix, right? Because this is an x is m by 1 vector, y transpose is 1 by n vector. If I multiply them, I certainly get m by n matrix, right? If it wasn't, I couldn't even define this minus, right? Doing minus, try and MATLAB doing minus and matrices have different dimensions, all you get is an error, right? So then I can subtract it, and then I can compute the Frobenius norm. Do you remember the Frobenius norm? I hope you do. That's just, you don't? Okay, so let me... okay, that's a problem. So the Frobenius norm of a matrix X, let's do it like this. So that's basically the square root, if I go over all elements, xij squared, okay? So typically what you want to do is just put the square here to get rid of the square root. So basically it's the generalization of Euclidean norm of vectors to matrices. Just I'm sure we discussed this. The other way you can write it, and that's actually what we're gonna need, is so the squared Frobenius norm of X, you can also write it as trace of x dx. Okay. If you think about it for a second, that's exactly the same thing as this. Okay, so intuitively the Frobenius norm essentially just tells you the magnitude of the matrix. Okay, if it was a vector, that would be just, but if it was a vector, you can also apply Frobenius norm, and then you're just down to ordinary Euclidean norm. That's clear, I hope. The other way you could look at it, that you vectorize the matrix X and then compute the standard Euclidean norm. Many different ways you can look at this very simple concept. So what this optimization problem is asking us to do? It's asking us to find an x and y such that, what does this mean, the difference between a and xyt? That's the key. Let's think about it. So that basically means the Frobenius norm is going to be minimized. The smaller the elements will be, right? The sign doesn't matter because the sign gets cancelled by squaring it, right? The smaller these x's will be, the smaller the elements of this entire matrix will be, the smaller the Frobenius norm is going to be, right? So all this is asking us to do is to find an outer product matrix xyt which is as close as possible to A. Okay, so basically we want to approximate A as an outer product matrix using the x and y vectors. Okay, so you could give it some practical-ish application. Like, imagine that your A matrix is, for example, 256 by 256 image. I guess that's like an old school. These days it would be more like 496 by 4096 image, but these numbers don't matter. Imagine it's an image, right? So the A matrix actually, the values in the matrix encode intensities of some image, okay? So what this is asking you to do is to do a brutal lossy compression of that image, okay? Because how much memory do you need to store this image? Is it 256 by 256? How many numbers do you need to store that? Some 65,000, right? 65536 or something like that. If you want to approximate by outer product, if you want to approximate it by some x, y, t, how much memory do you need to store the vectors x and y here? So this would be 65k. This would be 512 values, right? So it's pretty dramatic compression, right? Now I can tell you the quality is not gonna be beautiful. You will get nothing. You won't get anything like this, but you will get the rank 1 matrix, which is as close as it gets to that image, which is sort of cool, right? So you'll see something from the. If it was not a complicated image, it was like some sort of like low frequency image. Maybe you could actually get pretty close with that. I said this is a rank 1 matrix. I hope it's clear to everybody that's a rank 1 matrix. If not, you have a lot of studying to do before the final. And I also was saying that before. Okay, so let's solve this optimization problem, and I promise you that once we solve it, we will see immediate connection to SVD. Okay, so basically, like, this is a different path how you can arrive to SVD. So the path we took before was sort of like the hardcore linear algebra one. We were looking at subspaces, right, analyzing the matrix. Here, I'm asking you to solve an optimization problem, quite interesting optimization problem, if you ask me. And it will actually lead to the same thing. That's the spoiler. All right, so let's try to solve it. So let's solve an optimization problem. So we will start by rewriting the objective, okay? So it certainly doesn't matter if I'm gonna be minimizing instead this, right? So minimizing this is equivalent to minimizing this, right? If I scale it by 1/2, that's just for convenience. If I square this because this was a non-negative number, that's again just for convenience. Because it's a monotonic function, we'll do the same thing, okay? So next I will use this property that I can write the Frobenius norm as a trace of x dx. So in this case, it's gonna be what? It's gonna be 1/2 of, let me do it slowly to make sure I don't make any mistakes. So that's gonna be, I already made a mistake, see? So that's gonna be 1/2 of the trace of a minus xy transpose, the whole thing transpose, a minus xy transposed, okay? I just applied this to rewrite the Frobenius form. Because with traces, there are all these cool properties, which I have told you before, which are going to be useful now. Okay, let me make this a little bit slower so you can follow that interactively, I guess. So this I can write as A transpose minus YX transposed, right? Please check on me. YX, yeah. I just transposed the whole thing, and here is A minus XY transpose, all right? So let me expand the product here. So here I will have trace of ATA. Here I will have, what I will have here? So minus ATXYT minus YXTA, and finally, minus YXTXYT. I have to be careful about the order because I cannot be like willy-nilly about it. Or did I make a mistake?
You said minus in the plus initial extension. I thought in the last term.
Yeah, there should be plus. What did I say?
You said minus. I wasn't sure.
Okay, so I meant minus minus. Yeah, that's this one times this one, right? So the minuses go away. Thanks there. So now I know that the sum of traces is trace of sums, right? So I can split this. So I will get 1/2 of trace of ATA. And that's basically a constant, right? That doesn't even depend on x and yt. So that's the least of my concern here, okay? Then I'll have 1/2 of trace. Okay, let me do it slowly. So I guess I will have minus here and trace of ATXYT, and I will have another minus 1/2 trace of YXTA, okay? And here I will have plus 1/2 of trace YXTXYT, all right? So let's look at these terms. So the trace has this funny property that I can be flipping the multiplication. Okay, so I can do YTATX, and it's gonna be exactly the same thing. Again, if you don't remember that, you have to go back to the previous lectures where we talked about this. Same thing I can do here, so this is gonna be XTAY equal to this, right? Because I can take the y, I can put it here. The trace is not going to change if I do that. Now notice this is just a number. XTAY, that's a 1 by 1 matrix, aka number, okay? Same thing here, right? So here I can as well, so this is equal to, I can also transpose it, so this is x transpose AY. Aha, that's the same thing, right? Conveniently. So here, okay, so this is a constant, so I'm not gonna bother about it, I'm just gonna write a constant. And here I have minus 1/2 this, minus 1/2 the same thing, so that's just minus XTAY. All right, are you cool with that? Now what about this term here? I can again apply some trace magic to it, right? So what I can do, I can write this as XTX and YTY, all right? And then I can apply associativity, and I can write it like this. But again, this is a number, and this number is nothing but the square norm of x times the square norm of y. Everybody follows? Somebody. Oh, that's good. So this is plus 1/2 the square norm of x times the square norm of y. Okay, just basically doing algebraic manipulations to this expression. Did I get the minuses correct? I think I did, yes. Okay, so let's take a step back. What I was doing here is I was just simplifying this objective, this thing we are minimizing here, okay? And I converted it to this form. So there is some constant which doesn't bother us as far as the optimization is concerned, because of course the only thing that matters are the terms that depend on x and y, okay? And I want to be minimizing this function. By the way you can be looking at it, this is basically a function going from Rm times Rn to R, right? This is a function which takes x and y as arguments and produces some number, okay? Takes x and y. This is just a scalar, this whole thing, right? Just like the Frobenius norm was a scalar. So the problem here is to minimize this particular function. And of course, instead of minimizing f, it's equivalent to maximizing minus f, right? That's just basically just I was saying minus is plus, right? So basically I can be maximizing XTAY minus 1/2 of the norm x squared times the norm y squared, okay? I just flip the sign and I can, instead of minimizing, I can be maximizing it. Why not? Seems to make a little more sense that way. Okay, so how do I do that? How do I maximize this? So notice that this is an unconstrained optimization problem, right? It's a multivariate function, and I need to compute its maximum. So from what would you do knowing calculus? Well, the classical recipe is to compute the derivatives and set them to 0, right? This will give you critical points, which are the suspects for being a maximum. Okay, so let's do exactly that, because that's gonna give us something quite interesting here. So this is our, let's say that this is our function. Let's say this is function g. Okay, function g with exactly the same signature, Rm Rn to R. And what I need to do, so this is my function g, and I need to compute the gradient with respect to x of g. So the function g has two parameters, x and y, both are vectors, okay? X is an m vector, y is an n vector. So if I differentiate the function with respect to x, what do I get? I get ay, and here, so the y is constant as far as when I'm differentiating with respect to x, right? So nothing is going to happen to y. The square norm of x, that's just x dx, okay? So if I differentiate it, I get 2x, but the 2 cancels with the 1/2. So here I get just minus x square norm of y. That's why I basically introduce the 1/2 here, so it cancels later. That's just a convenience type of thing, okay? If I compute the gradient with respect to y, it's going to be very similar process. Here I will get A transpose x, and here I will get y x squared. Again, I'm differentiating with respect to y, so nothing is going to happen to x, but only the y's get differentiated away. This is just a quadratic, or, well, it's a polynomial in x and y. Okay, so the gradients are quite simple. So what we need to do now is set them to 0 and examine the critical points. Okay, so let's try that. So that means that this thing will be 0. So that means that we are looking for y and x such that this is true. And if I set this to 0, I want these two things to be equal, right? I just put there equals 0, and this is what I get. These two, I mean, already these are systems of equations, right? It's a bunch of equations, another bunch, but I have like two different bunches here. That makes sense. By the way, is this starting to look familiar? Because I could write this equivalently as just transposing everything. I could just write this like this. Is this starting to look familiar? Okay, so I need to solve this system of equations now. Okay, so let me do one slight trick to introduce a little substitution. Basically, instead of solving for x and y, I can write them like in polar form, if you will. So I can say that, let me do this substitution. Instead of x, I'll be looking for alpha x hat, where alpha is a scalar, actually non-negative scalar, I guess I could do this, and x hat is a vector of norm 1. Okay, so basically what I'm doing here, I'm splitting the unknown x we are solving for into the magnitude and a unit vector. Okay, I can always do that, right? Any vector I can write using the length of the vector and the unit direction. Turns out that this will actually help us here. I can do the same thing to y. Okay, so I can write y as beta times unit version of y. Okay, normalized version of y. Okay, so this is a substitution which I'm gonna use. So let's just substitute it in there. So what I will get is a beta y hat equals, so x is alpha x hat, right? And y squared is beta squared, right? Let me substitute it here too. So this will be a transposed alpha x hat, and that equals beta y hat, and the norm of x squared is alpha squared. Okay. So I have some opportunity for cancellation, right? So I can just divide by beta here, and I will get a y hat equals alpha beta x hat. And here I can divide by alpha, and what I will get is this. I will get a transpose x hat equals alpha beta y transpose. Okay, everybody sees that? Did I forget something somewhere?
I think you said y transpose.
No. It's written correctly at least. Whatever I said,
Yeah.
that doesn't matter. I can be saying things. So this is actually sort of interesting if you think about it. These degrees of freedom alpha and beta is essentially turned out that they are coupled, right? Because essentially you don't have to be solving for alpha and beta separately. You can just be solving for alpha and beta together. So, and the alpha is just the magnitude of x, and the beta is just the magnitude or length of y. Okay, and actually makes perfect sense. If you go back to the statement of the problem, you can like immediately notice that it doesn't really matter where if I put the scale on x or on y, right? Because if it's just multiplying it, I can be multiplying either x or either y. It will just be multiplying the entire outer product matrix, right? In other words, I don't really need, it's sort of like a luxury to have a scale on both x and y. I don't really need the scale on both, because at the end of the day, I just multiply them through. So I need only one global scale on the entire outer product, right? So this alpha times beta, that actually totally makes sense, right? It makes so much sense that I will introduce another substitution. I will just say that alpha beta equals gamma. Okay, so, and I'll say that the gamma is a new unknown, like another substitution. So if I do that, that's an easy substitution to make, right? So if I do that, I will get the following system to solve. So a y hat equals, so this is just the gamma, x hat, and a transpose x hat equals gamma times y hat, okay? Now does that look familiar? Exactly, so that's going back. That's basically asking for the x, y, and gamma to be left, right, singular vectors and singular value, right? But since we are like, let's pretend for a little bit we don't know anything about SVD, and let's just like continue solving this problem. So let's just do that, okay? So how do I continue? So I got to this system of equations. How do I solve it? Well, for example, I will express from the second equation, I'll express what is y hat, right? So y hat is just 1 over gamma a t x hat, nothing terribly special there. And I plug this y hat into the first equation, right? I can totally do that, right? So what I will get, if I do that, I get 1 over gamma a from here and a transpose x from here, and that must be equal gamma x hat. Okay, everybody got that? I took y hat from the second equation and I substituted it for this y here in the first equation, or I guess vector equation or system of equations if I was to be accurate. The one thing you need to be careful about is the order, but here is AT on the right and A on the left, so this is going to be AAT, okay? So this is AA transpose x hat equals gamma squared x hat. And we are back to what we already knew. We are back to eigendecomposition, right? So here it means that in terms of this optimization problem, the critical points, at least in terms of the x, are very closely related to eigenvalues and eigenvectors of the matrix AA transposed, okay? So basically every eigenvector of AAT corresponds to a critical point of this optimization problem, okay? Now it's not the full story, right? So what I would do now if I was solving this problem, I would compute the eigendecomposition of AA transpose, right? Again, we know that's a symmetric matrix, that it's positive semi-definite, so we know that the eigenvalues are, that's actually sort of important, right? We know that the eigenvalues are non-negative, and that's why this sigma squared makes sense here. Because that means whatever eigenvalue I get, I can take the square root, and that's going to be my gamma, okay? But we know that AA transpose is always positive semi-definite, at least. It could also be positive definite, so this is cool. That's going to work. And once I have computed the eigenvalues sigma, sigma I, and xi hat, then I can go back here, because if I already know the gamma and x hat, I can immediately compute the y hat, right? I could also go the other way around, actually. Let me do that, just to show you the full picture. I could express x from the first equation, right? So I could write this. I could say that x hat equals 1 over gamma a y hat, plug it into the second one, okay? So I would get 1 over gamma a transpose a, again the order matters here very much, and here is y hat, right? Because I'm substituting this x hat into here. and that equals gamma y hat. All right. So again, I multiply by gamma, and I will get a t a y hat equals gamma squared y hat. So we are essentially sort of like rederiving what we already knew, I hope, about SVD. That's saying that this y's, at least in the context of this problem, interestingly, so the y's are the eigenvectors of the matrix ATA. Okay, and the gammas, again, same story, right? ATA is going to be symmetric, at least positive semi-definite, so the eigenvalues are guaranteed to be non-negative. I can take the square root. You can also immediately see that the gammas are in correspondence. Okay, so that's quite cool. So that already showed how to compute the critical points of this optimization problem. Okay. But we are still not completely done actually minimizing this, right, or maximizing this reformulated problem, because the critical points are just the suspects, right? I think the theorem goes like this. It says that if a point is extremum, it must be a critical point. It must have the derivative 0, right? But you cannot always flip it the other way around. So what we are gonna, but we have all the critical points. If I find all the eigenvectors, if I can find all the suspects, right? I can find all the eigenvectors of AAT, all the eigenvectors of ATA, or I don't even have to do this, right? I can just find all the eigenvectors of AAT and then compute the corresponding y's like this. And then the pair of x hat and y hat and the scaling parameter sigma, that gives me the critical point. Okay, if I want to be really precise, then I have to retrieve from the substitution, right? Because so far, this way I only compute the gamma. Okay. What I actually need is the alpha and beta, right? And there is, it's ill-posed. It's not uniquely specified. How shall I split the gamma into alpha and beta? I can do this in many ways, right? If I'm given a gamma and I have to come up with alpha and beta, they better be non-negative, of course. But so the simplest way to do that is to just say that alpha is the square root of gamma and beta is also just the square root of gamma. Okay? Then I can say that my critical point for the original optimization problem, retrieving from the substitution, remember that was alpha x hat, and the critical point y, that was going to be beta y hat, right? The x hats and y hats, that's exactly what I computed this way. So, so basically this is the square root of gamma x hat, and y is the square root of gamma y hat, okay? And this pair x and y, the square root of gamma x hat, square root of gamma y hat, that's my critical point. Now my question is, which one is the best? Which one is actually the true minimum of that problem? So let's just try. So after the reformulation, we reformulated the original optimization problem into maximizing xtay minus 1/2 square norm of x and square norm of y. Okay, so let me see if I can arrange this so you can see everything. So let's just take the, oh, and by the way, I can, by the way, this is, if I'm computing it this way, then this y, so this will be square root of gamma, and this y hat is just 1 over gamma ATX hat, okay? Which is nothing but what? 1 over square root of gamma ATX hat, right? Because it's the square root of gamma times square root, so 1 over square root of gamma ATX hat, okay? Well, let's compute what is the objective in each of these, okay? So if this is an n by n matrix, then the AAT, then I will get and it's all the eigenvectors, the standard stuff applies, it's symmetric, so all the eigenvectors exist. It's no such thing as a defective matrix, so I will have n eigenvectors, right? I could be calling them xi and xi hat if you wanted, and gamma I, but let's not do that. So what we need to do is to compute the actual value of the objective, okay? So what is the objective for each of these x hats and gammas? Well, if I just plug it in there, so I will get, so my objective is let me just copy it here, xta y minus 1/2 square norm of x square norm of y. So how much is it if I substitute this? So this is gonna be square root of gamma x t a, and the corresponding y is 1 over square root of gamma a. Wait a second, thing wrong. What am I doing wrong? That's exactly the point in the lecture when I start making mistakes. But this should be easy enough to find out. I think I need to think about this differently. So I take this, and what I plug in here is the substitution. Where is that? Here. So my x is alpha x hat. So let's try that way. So that's gonna be alpha x hat transposed a, and y is beta y hat, and this is minus 1/2. So the x in this parameterization, the square norm of x is just alpha squared, and this is just beta squared, okay? So, and because my gamma is just the alpha times beta, that's what's here, so this is going to be just gamma times x hat t a y hat minus 1/2 of gamma squared. Okay. Now the interesting thing is that ay that you can see here, ay is exactly gamma times x hat. That's what we had here. Gamma times x hat equals ay. Okay. So if I use that, this is just gamma squared x hat transpose x hat minus 1/2 of gamma squared. But how much is that? Let's not confuse it with this. This is a unit vector. That's what x hat was. Okay, so this is just a gamma squared. This is just 1. This is gamma squared minus 1/2 gamma squared, which is 1/2 of gamma squared. Okay. And what was the gamma? The gamma was the eigenvalue of AAT. Okay. So the value of the objective, which I'm trying to maximize, is exactly 1/2 of the square of the eigenvalue of AT. Okay, so if I want to maximize the objective, well, what do I want to pick? Well, I want to pick the eigenvalue, the maximal eigenvalue, right? Then I have maximized this, and that's the answer to my optimization problem. If I want to solve this optimization problem, I form the matrix AAT, and I compute the eigenvector corresponding to the largest eigenvalue. Similar to what you are doing now with the paint ring, so similar type of idea. From that, I can compute the y, right, using this relationship, which I used here. Oh, this one actually. This one. And that's the solution. So that would be sort of cool So did you get that? So that's the cool thing is that this is basically like an optimization approach to SVD. By solving this variational problem, you essentially arrive again at SVD, which tells you like another interpretation of it. So if you, that would be actually a fun little project if you wanted to do another project, if you didn't have enough. You can just try it on an image. Try it on a bunch of different images, and you will see what rank 1 approximations of that image you will get, right? And if you do that, you will find out that the rank 1 approximation is not particularly interesting. So then you might be asking yourself, well, what if I want to do rank 2 approximation? Or rank 3, right? In general, low rank approximation, which is sort of a cool topic nowadays when we talk about big data a lot, because these low rank approximations, they take much less memory than some huge matrices, right? Especially if you like mix it with sparsity, that's like pretty cool topic in machine learning and statistics. But let's just talk briefly, if we were to generalize this from rank 1 matrix to rank k matrix, okay? I think I have a slide on this. This goes back to what we talked briefly about last time, that essentially the SVD you can write as the sum of outer products, okay? Each of the matrices contributes rank 1, so all together this will be a rank R matrix. So again, this is so I take a matrix A, I compute its SVD, so sigma are the singular values, U's are the left singular vectors, V's are the right singular vectors, and the product U sigma Vt, I can rewrite using this sum. We discussed why last time, right? It's not very difficult, just rearrange the terms in this matrix product. Now, interestingly, if you want to find, so if this is my matrix A, and I want to find a matrix AK such that I minimize the Frobenius norm of this, such that the rank of AK equals K, the solution can be immediately obtained from SVD, okay? What we have done before, what I've shown you, what I've actually derived, like from basic principles, this whole stuff, solving this optimization problem, that basically told you that if you are looking for rank 1 approximation, what you are gonna do, you are gonna keep only this guy there, discard everything else, okay? That's basically what we arrived to. So it should come as no surprise that if you want to do optimal rank 2 approximation, what do you think we're gonna do? Well, we're gonna discard everything but the first 2 terms, and we get the optimal rank 2 approximation, okay? And that would be actually another cool, nice project to do this with an image, okay? But I'm afraid I'm not allowed to assign any more projects. Because it's cool that you keep increasing the rank of the approximation, and it will quickly approach to the original image. You might be actually surprised how good compression you can get. It's not gonna be as good as JPEG or something like that, but it's a little bit different. It's also interesting. For some images, actually might be better. This is this result is also known as Eckart-Young theorem. So I think these guys were one of the first ones who realized this. So if you are looking at the SVD, it's actually like really simple. Basically, the SVD already tells you how the optimal rank R approximations look like, right? All you need to do is go and zero out these sigmas. By the way, if you are looking at real data, if you are looking some like interesting real data, whatever you'll be working with, I don't know if you'll be like in biology and analyzing, I don't know, bacteria, or if you'll be in like car company analyzing tons of data about cars, something and you have observations, and you put the observations as columns of matrix A, you're gonna get a huge matrix A, right? Once you have a huge matrix A, the first thing you would be interested in is computing the SVD, which tells you a lot about the data. I guess I have another example on that, but okay, yeah, okay, let me show you this bare example. SVR edit. So here is a specific example, like simple one. So here the story is that you are a biologist and you are measuring heights and weights of a bear population, okay? So your data samples are just size of 2, okay? So that's not a lot of measurements. You probably want to take more measurements once you have captured a bear. This is a toy example anyway. And you assume you have like captured like a large population of bears, okay? And you suspect that there is a correlation between the two, okay? That the height of a bear is strongly correlated to its weight. The way you can discover it very easily using MATLAB is you just form a matrix of these observations and you just hit SVD, okay? In MATLAB, this is really just typing SVD of A, and I mean you have to store the result somewhere. It's like one line really in MATLAB. And then you look at the singular values you got back. Yeah. So here it's just like 2 by n matrix. So there will be just 2 singular values, okay? And if the second singular value, the sigma 2, is close to 0, then you know something interesting is going on. Then you know there's probably some relationship in the data. There's probably some relationship between height and weight. Okay, in that case, you would probably be guessing it already, right? You would be already expecting that sigma 2 is going to be close to 0. If the sigma 2 is significant, if it's bigger, if it's like 0.00016 or something small, then probably it's almost rank 1 matrix. Okay, so that means that there is very tight relationship between these. So in other words, SVD lets you quantify the rank of the matrix, okay? If you were looking at some more realistic example where you will be measuring tons and tons of attributes of some entities you are measuring, then you would have tons of dimensions. And if you just plot the spectrum of the single values, you might see interesting things, right? You might see that the spectrum is like significant at first, and then it drops suddenly, and then the remaining ones are like really small, right? So this tells you that there is something in the data which is about this dimensionality, okay? If you see clustered singular values, that again signifies that there is something special going on in the data. And if you actually think about your problem hard enough, you might find out what that was. Typically some symmetries in the data, okay? Like we were doing it before when I was at Disney, we were doing it on, or Peter Bike was doing it on spherical harmonics, like computing lighting, and it was on a sphere. And it turned out that if there are some symmetries on the lighting patterns on the sphere, that reflected as repeated single values here. So this is actually sort of cool, like even like a machine learning tool or analysis tool, like or data science or whatever these things are called these days. They keep renaming it. It used to be just called statistics, right? But now it's like machine learning and big data and all these things. But it's still the Eckart-Young theorem is like from the 30s or 1930s or something like that. Yeah, so if the sigma 2 here, back to the bear example, I digressed a little bit. If you find that the sigma 2 is small, then the plot probably looks like this, that the data maybe are not exactly on a line. It's not a perfect linear relationship because there's going to be some outliers and noise, right? You might have an outlier here, right? Some, I don't know, sig bear or something. But mostly it should be like a one-dimensional type of thing. So PCA essentially is a different perspective on SVD. It's the mathematics is essentially the same, but it's more like a slightly different interpretation you give it. Like I think this is more used in like the statistics community, and SVD more like if you are talking to like linear algebraists. But essentially the key idea is the same. So but PCA, one way you can look at PCA in more like the statisticsy type of way. So if I have some, again, just in 2D example, if I have some observations, some data, again, it's 2D, so it's like that simple. So the first principal component is the vector, such that when I project all my data on the vector, I get maximum variance. Okay, you can see I'm sort of using like a statistical terminology because that's what's typically used there, but you can express it just in the language of linear algebra. And if your A matrix has data in columns, all you need to do is compute AA transpose and find the leading, the eigenvector. By leading, I mean the eigenvector with the largest eigenvalue. That gives you this vector, the principal component. What you do in PCA, you typically subtract the mean, so you are nicely mean-centered. That's something that you typically don't do in SVD, but those are like really nuances. The key stuff, looking at the eigenvectors of this covariance matrix. Again, in statistics, they would tell you this is a covariance matrix, and would tell you lots of like statistics story. But the point is looking at the eigenvector, which tells you something cool about your data. By the way, if you remember the, what was it called? The total least squares problem. Was it total least squares? When we were looking, what's that called? We were looking for the best fit line, right? Where we were essentially searching this vector a couple lectures ago. This vector was the eigenvector of AAT corresponding to the smallest eigenvalue, okay? In this case, we are just in dimension 2, so there is just 2, right? Because then you exhausted the dimensions already. So the first one must be the principal component, the second one must be the least principal component, or the least component. I don't think this is an official terminology. But the point is this works beautifully on high dimensional data. Okay, if the data have 100 attributes, that's absolutely no problem, because if the matrix A, if your data matrix is what it is, it would be D times, D is the dimension of data, and N is the number of data, okay, number of data samples. Almost always you have a lot of data, more data than attributes. If you have more attributes than data, then you probably have to go collect some more data. Again, that's very popular today. So if you form AAT, then the matrix is gonna be D by D, okay? So if you had like 100 attributes, no problems, it's gonna be 100 by 100 matrix. That's the cool thing about the covariance matrix, that the number of data essentially disappears, interestingly enough. And my point was that if this is a 100 by 100 matrix, then computing the eigenvectors of it, that's no problem, right? In MATLAB, that you get the solution immediately. So the 2D is just like a toy example. Even for a much larger, you can compute it efficiently. So in summary, PCA discovers linear relationships in data. It has, don't think it's a panacea. It's not a cure-all. If you have data, which, for example, you could have data that do something like this, right? Maybe some outliers somewhere here. If you have data that look like this, PCA is not going to discover that this is essentially a circle, okay? To do that, you would need some nonlinear dimension reduction techniques, but that would be an entirely different story. Not entirely, the linear algebra is still important there, but that would be an advanced topic. What PCA would discover for you, if this was, for example, embedded in some higher dimensional space, would discover for you the plane where the circle lives. Okay, if you were in 100 dimensions, you happen to have a circle there, PCA would happily find for you the plane, the hyperplane, where this circle lives. But it would not discover for you that it essentially is a circle. Okay, so I think that's a good thing to conclude with, unless you have some questions. All right, so I guess I'll see you next Monday, but somewhere else and doing something else, aka final exam. All right? Okay, well, thank you all for coming.